Okay, hello. Today we are going to look to an example of how to solve the Hamilton-Jacobi equation for another mechanical system using a very famous method in this topic, which is known as the method of separation of variables. So the example that we are going to use is a particle that is in a uniform gravitational field. So we know that if the gravitational field is uniform, the Hamiltonian that is going to correspond to this particle is going to be the next. It will be h equals px squared plus py squared, all divided by 2m. In this case, we are considering the motion of the object in 2 dimensions because it will have a kinetic energy associated with the velocity in the x direction and in the y direction. Okay, and then a potential energy that corresponds to mgy. Okay, perfect. Of course, this mass is this m is the mass of the particle, and g is the acceleration of gravity. So we remember that the Hamilton-Jacobi equation says that a function h, which is a function of, in this case, we have two generalized coordinates q, which is going to be qx, qy, px, py, and the time. And of course, in our case, we consider qx just as x and qy as y. Okay, we have generalized coordinates for position and coordinates for the momentum that correspond to those generalized coordinates of position. And then we sum the partial derivative of s with respect to time, and this needs to be equal to 0. Perfect. So looking that we have two elements of conjugate momentas, we need to write them in terms of the partial derivative of this function s with respect to some generalized coordinates. Of course, in this case, we know that px is equal to the partial of s with respect to x, and py is equal to the partial of s with respect to y. So that means that the Hamilton-Jacobi equation takes the form h of x comma y comma the partial of s with respect to x, the partial of s with respect to y, the time, plus the partial of s with respect to time equals to 0. So that will be the Hamilton-Jacobi equation for a particle that is under a uniform gravitational field. And what happens if we take this Hamiltonian and we take the values of px and py into it, which correspond to the partials with respect to x and with respect to y? Well, we are going to get that we will have 1 over 2m that is going to multiply the partial of s with respect to x squared plus the partial of s with respect to y squared. Okay, so yeah, and then plus mgy plus the partial of s with respect to time equals to 0. So this will be the Hamilton-Jacobi equation for the particle in a uniform gravitational field. Perfect. Look that we have replaced the positions of px and py for the derivatives of s. Perfect. So the method that we are going to use consists in taking a function that is going to be of the variables x, y, t, and express it as the sum of 3 functions of one variable. For example, a of x, b of y, and c of t. Look that these functions, well, they are of just one variable. This a only depends on x, and this b only depends on y. So we are going to propose a solution for this equation given by this expression, and we are going to see what happens. Well, of course, if we calculate the partial derivative of s with respect to x, looking that only a depends on x, we can set that this is equal to the derivative of a with respect to x, the total derivative, because of course a only has one variable, so we can just take the total derivative, and that will happen the same with the partial of s with respect to y, that will be equal to the total derivative of v with respect to y, and the derivative of s with respect to time will be equal to the total derivative of c with respect to time. Perfect. So we can take this into the differential equation to get that 1 divided by 2m multiplies the derivative of a with respect to x squared plus the derivative of b with respect to y squared plus mgy equals, and let me take these into the right hand side of the equation to get minus the derivative of c with respect to time. Perfect. And something that I want you to notice here that is very common when you use a separation of variables method in differential equations is to notice that the left expression on the equation is a function of some particular variables and the right hand side of the equation is a function of other variables. Yeah, this is very, very common in solving differential equations that are partial differential equations. So we can say that this can be seen as a function of x and y, while this is a function of t. So what happens if we have the derivative of a function of t in the side, and then here we have a function of x and y, which are different variables? Well, that means that, well, all this expression on the left hand side needs to be equal to a constant, and the same thing happens with this element that we have here. It has to be equal to a constant, because if we have a function of different variables that are equal, they can only be equal if they are constants. Okay, so if this thing over here is equal to a constant, well, we can set easily that c of t is going to be a solution. Well, it will have the form minus p1t, where p1 is a constant. Okay, we have just encountered the solution for c, taking well, yeah, we had that the derivative of c with respect to time is equal to a constant. If we take the integral, then we get that this is equal to a linear function of t. Perfect. And actually, you will have to notice in some further examples that this thing that we have here, which is a linear function, will occur very often if, for example, this t does not appear on the Hamiltonian. So what I'm saying is that looking at the t doesn't appear here in the Hamiltonian, then this function c in the separation of variables proposal, well, is a linear function. Okay, so the t is not in the Hamiltonian. That means this c is a linear function. Perfect. Okay, so looking that this was equal to a constant, then again the left hand side of the equation is also equal to a constant. So what is that constant going to be? Well, looking that we name this as p1. Of course, if we take the derivative of this, we get minus p1, but minus the derivative of that is just p1. So that means that we can set 1 divided by 2m times the derivative of a with respect to x squared plus the derivative of v with respect to y squared plus mgy is equal to p1. Perfect. So what we are going to do next is to solve this equation for the derivative of a with respect to x. So we are going to get the derivative of a with respect to x squared is going to be equal to, it will be p1 minus mgy, and then this multiplies 2m minus the derivative of v with respect to y squared. And with the same explanation that we gave before, this is only a function of x and this is only a function of y. So if we have two functions of different variables on both sides of the equation, that means that they need to be equal to a constant. Okay, so what we are going to set is that we will have that the derivative of a with respect to x squared will be equal to, well, maybe p2 squared, taking that the derivative of a with respect to x will be seen just as a constant p2, and making that a as a function of x will be equal to p2x. Perfect. Let me close this, and also let me close the solution that we found for the c. Okay, perfect. So this takes us to get that, well, the derivative of a with respect to x is of course p2, and the derivative of a with respect to x squared is p2 squared. Okay, so getting back to this equation, we are going to get that p2 squared is equal to p1, and let me multiply by that 2m, this 2m p1 minus 2m squared gy minus the derivative of v with respect to y squared, like this. So now we are interested in finding a solution for the derivative of v with respect to y. So if we work a little bit, we are going to get that the derivative of v with respect to y can be seen as plus minus the square root of 2m p1 minus p2 squared minus 2m squared gy. So yeah, the thing here is that, well, we do not have to care about these two signs. We can only choose one, looking that we are looking for one solution. So there is no problem if we just take into account the positive solution. So if we remember, the solution proposed was a plus b plus c. So that means, and yeah, let me establish that b is equal to, well, the integral of the square root of 2m p1 minus p2 squared minus 2m squared gy dy. So this takes us to establish the solution s equals to, well, a of x, with that was a p2x, and then b of y, which is this integral that we have here, 2m p1 minus p2 squared minus 2m squared gy dy, and then plus c of t, but that was equal to p1t. Perfect. So now we have found a solution for the Hamilton-Jacobi equation as the sum of three functions that are of just one variable. Okay, perfect. Remember that on the first lesson that we have given in Hamilton-Jacobi formalism, we established some equations that the function s needs to verify. One of those equations is that pi needs to be equal to the partial of s with respect to qi, where this pi is the little p. Don't get confused. Remember, we have little p and upper p. So the other equation was that the upper q is equal to the partial of s with respect to the upper pi. Okay, these are the equations that we showed on that first lesson. In this case, I goes from 1 up to 2, and they are equivalent to the x and the y. So that means that we are going to consider that here is going to be px, which is going to be the partial of s with respect to x. And with these q's, we are going to remain with the number notation, okay? So that means that this will be q1 equals to the partial of s with respect to p1, and the other equations will be py equals the partial of s with respect to y, and q2 will be the partial of s with respect to p2. So with these equations and with the solution that we found, we are able to find px, q1, py, and q2. So px, if we take the derivative of s with respect to x, looking that this element does not have an x and this element does not have an x, that means that the partial of s with respect to x is only going to be this p2 that we have here. So the first result is going to be that px is equal to p2. Recall, this is little p and this is upper p. Perfect. So what happens with, for example, py? Well, py is going to be equal to and let me close this. Py is going to be the partial of s with respect to y. So this one does not depend on y. This one does not depend on y. So we just need to take the partial derivative with respect to y of this element that we have here. But looking that we are taking the derivative of an integral, looking that they are inverse operators, well, we are just going to make that we cancel the integral, like if that is the correct way, maybe. So that means that this py is going to be equal to what is inside the integral. So that means that we will have here the square root of 2m_p1 minus p2 squared minus 2m squared gy. Perfect. So this will be the value of little py. Okay, so what we are going to do now is to calculate what is q1. Well, we need to take the partial derivative with respect to p1 of this integral that we have here. So this will be equivalent to the integral of the partial derivative with respect to p1 of that square root that we have there, which I'm going to write like this: 2m_p1 minus p2 squared minus 2m squared gy dy. Yeah, I just switched the order of the integral and the derivative because that is legal, don't worry. So, and yeah, this is raised to the 1/2 power. So let me take the derivative. This will be the integral of 1/2 2m p1 minus p2 squared minus 2m squared gy to the negative 1/2, and then the derivative with respect to p1 of what is inside due to the chain rule, which is just going to be 2m. So this 2 cancels with this 2. We got dy here. So that means that q1 is going to be equal to the integral of m divided the square root 2m p1 minus p2 squared minus 2m squared gy dy. Okay, and look here that, well, the function s that we found has a p1 here and a p1 here. So we still need to take the partial derivative with respect to p1 of this, which is just going to be a t. Well, a minus t, actually. So that means that we need to add a minus t here, a minus t here, and a minus t over here. And I'm not going to solve this integral because, well, I think that is not necessary. But I'm going to tell you what is the result if you make this integral. Remember, it's just an integral of y. It shouldn't be so hard, but the result is that minus 1 divided by mg, the square root of 2m p1 minus p2 squared minus 2m squared gy. So this will be q1. Perfect. Okay, this is q1. So we are going to calculate now q2, which is the partial of s with respect to p2. So it will happen something very similar. Here we have an element that depends on p2, so the partial with respect to p2 of this element is going to be x. And then we need to take the partial of everything of this with respect to p2. It's going to be very similar to the procedure that we just followed. So q2 is going to be equal to x plus the integral of the partial with respect to p2 of 2m p1 minus p2 squared minus 2m squared gy raised to the 1/2 dy. So again, we are going to calculate the derivative is x plus the integral of 1/2 times 2m p1 minus p2 squared minus 2m squared gy to the negative 1/2, and then times the derivative with respect to p2 of what is inside. So that is minus 2p2, and then dy. Perfect, so we get x, we cancel these 2's, plus the integral of p2 divided by the square root of 2m p1 minus p2 squared minus 2m squared gy, and then dy here. Perfect. Again, we are not going to solve this integral. If we do that, the video will be very long. So this is going to be equal to x plus just p2 here. That is going to divide m squared g, and is going to multiply the square root of 2m p1 minus p2 squared minus 2m squared gy. Perfect. This will be the result for Q2. So let me write you these 4 results here in this page. These are the 4 equations that we just found. Remember that before introducing the Hamilton-Jacobi formalism, we were talking about some canonical transformations that they need to accomplish, that they are functions of the generalized coordinates and the conjugate momentas. Remember that if we find a canonical transformation, that is equivalent to say that we have a new function q and a new function p that are functions of the q and the p, and yeah, only functions of q and p. That happens the same with the p. Okay, but in this case, we have found these canonical transformations, but look here that, for example, this q depends on the upper p, the upper p1 and the upper p2 actually. So we do not want that. We would like to have a function q1 that will be only a function of maybe y and maybe x and the time, okay, but not a function of the upper p. So we need to solve these equations to get these kind of functions. You will see it in this example. So, for example, let's look at this first equation that we have here. We can see that this p2, this upper p, it is actually px, little px. So, with that, we can solve this equation for p1, and in that case, we will have a function p1 that will be only of the variables px, py, and y. So that is what we are actually looking for. So, what are we going to do? Well, let me establish this as py squared plus p2 squared plus 2m squared gy equals to 2m p1. Yeah? Okay? Yeah. And remember that this p2 is equal to px, so we get px squared. This is little p, remember. So it is easy to see that p1 is going to be equal to 1/2, 1 actually divided by 2m, times px squared plus py squared plus mgy. Okay, because remember these 2m will cancel these 2m that we have here. So we only get an m on the numerator. Perfect, so we have found the first canonical transformation for the upper p1. Okay, so with this value that we just found, we can find this q1 that we have here, because we know what is p1, we know what is p2, so we are going to substitute those values into that expression. So we are going to get that q1 is equal to minus t minus 1 divided by mg, the square root of 2m p1, but that p1 is going to be this that we just found, which is 1 divided by 2m px squared py squared plus mgy, like this. So that is 2m p1, and then we will have minus p2 squared, but p2 is px. So px squared minus 2m squared gy. Recall that for now, this function q1 is already a function of the generalized coordinates and the conjugate momentas little p and little q. So if we keep simplifying, we will get minus t minus 1 divided by mg, the square root of px squared py squared plus 2m squared gy minus px squared minus 2m squared gy. We can cancel this to get that q1 is equal to minus t minus 1 divided by mg and the square root of py squared. And we are not going to worry about the absolute value of the py. We're just going to take one of the values that will be perfectly acceptable. So q1 will be minus t minus py divided by mg. Perfect. So with this, we have found q1 in terms of the little p and the variable t. Okay, and let me write in this step that p2 as a function of these little coordinates is equal to px. So we are left with the q2 function, okay? So that is this one over here. We have now the p2, we have the p1, so we need to substitute that into this expression to see what are we going to get. Let me rewrite this equation. Okay, so if we substitute the values that we have found, we are going to get that q2 is equal to x plus p2, which is px divided by m squared g times the square root of 2m p1, which is 1 divided by 2m px squared plus py squared plus mgy, and then minus px squared, which is p2, minus 2m squared gy. Okay, so this is x plus px divided by m squared g. Here we will have px squared plus py squared plus 2m squared gy minus px squared minus 2m squared gy. This cancels, and we see easily that q2 is equal to x plus px m squared g, again py. Perfect, so that is the function q in terms of the little variables. So with this, we have now completed the transformation, the canonical transformation that corresponds to the particle under the gravitational field that is uniform. So remember that we mentioned that the Hamilton-Jacobi equation comes from thinking that these canonical transformations lead us to a new Hamiltonian that is equal to 0. And that means that the derivatives with respect to time of these new functions that we found are equal to 0, meaning that these functions are constants. So if we are able to express the the x, the y, the px, and the py in terms of these variables, looking that they are constants, well, those new functions will be equivalent to the solutions of the equations of motion of the mechanical system that we are studying. Okay? Let's say, for example, that we are able to express this x as a function of q1, q2, p1, p2, and the time. Looking that these are all constants, well, this means that we will have a function equivalent to x of t, which is, of course, the solution of the motion of the particle that we want to find. So this means that we need to find the expressions for these four variables in terms of the upper variables. So how are we going to do that? Well, by now we already know that px is equal to p2. So this means that, well, this is already an equation of motion. It tells us that the momentum in the x direction is a constant because p2 is a constant. Okay, this is the first solution that we have. Perfect. We have found also that q1 is equal to minus t minus py divided by mg. So we can solve this easily for py. We will get that py divided by mg is equal to minus t plus q1. So py is equal to minus t plus q1 mg. Okay, perfect. So this means that this is another equation of motion that is telling us something about the momentum in the y direction. The momentum of the particle, we see here that it is not a constant. It depends on the time, so it changes on time. And yeah, this can be seen as a function py of t. So this is the second solution. So what happens with the x and the y? Well, we found that the q2 that we have here is this equation, but we can set that this is q2 minus px py divided by m squared g is equal to the x. But we know that px is equal to p2, yeah, and py is all this thing. So that means that x is equal to q2 minus p2 divided by m squared g times py, but that is minus all this thing. With this minus is going to be a plus, and then mg t plus q1. So x is going to be q2 plus p2 divided by m times t plus q1. Perfect. Again, we have found x in terms of the time and some constants. So this is equivalent to say that this is the equation of motion in the x direction. Perfect. So we need to still find an equation for y, but remember we found that p1 is equal to py squared plus px squared divided by 2m plus mgy. So from this we are going to solve for y, and we get that, what are we going to get? We get that p1 minus py squared plus px squared divided by 2m is equal to mgy, but p1 remains the same, minus py squared. What is py squared? Well, it will be this thing squared, so it will be equivalent to write the next t plus q1 squared m squared g squared, and then plus px squared, but px is p2, so p2 squared. Okay, all this is divided by 2m, and this is equal to mgy. So we will get that y is equal to p1 divided by mg minus, okay, with this my dividing here, we will only get a g surviving at the numerator. So this will be t plus q1 g, and these two in the denominator, and then minus p2 squared divided by 2m squared g. And this term is squared, of course. So, yep, I think this is the final result. We have found a function of y in terms of the time, which is the solution of the particle in a uniform gravitational field. In this case, Remember, the P1 and the P2 are constants. So this is equivalent to the equation of motion in the y direction. Okay, perfect. So this will be the 4 results that are important in this lesson.